So in the last lecture, we have seen the definition of a continuous function, and we have seen some characterizations for the continuity of a function. Now the question arises, what are the examples of continuous functions on general topological spaces? On general topological spaces, so of course from calculus we know that we know a wide variety of continuous functions. So for functions f from R to R, so real valued functions on the real line, there are many examples of continuous functions. So for example, any polynomial is a continuous function. Polynomials are continuous. For example, the absolute value function is continuous. Absolute value function is continuous. Then some trigonometric. So let me just write some examples. So here explicit examples are fx equals 1 plus 2x plus x cube, something like this. Here fx is just the absolute value function mod x. This is a continuous function. And then some trigonometric functions are continuous. Trigonometric functions are continuous. For example, fx equals sine x or cos x. These are continuous functions. However, note that tan x is not continuous. Fx equals tan x is not continuous. Okay, so I leave it to you to think why this is so. This is an exercise to show that tan x is not continuous. And so now for the functions on real line, we have plenty of examples. So the question arises, what are the examples of continuous functions on general topological spaces? And in this lecture we will see some rules for constructing continuous functions for general topological spaces. So let us look at this theorem, and we will give different ways to construct continuous functions on general topological spaces one by one. So the first part says that constant functions are continuous. So what is a constant function? So we fix a point y not in Y. So of course we have taken x, y and z to be topological spaces, and we fix a point y not in a space Y, and then the function f from x to y, which takes every point to y naught. Okay, so fx equal to y naught for all x in X. This is a continuous function. Similarly, the inclusion functions are continuous. So by an inclusion function we mean when you have a subset given by a subspace topology on this subset, and then the map J from A to X, which simply takes a point to itself. So here on the left hand side you have an element in your subset A, and on the right hand side you consider it as a point in X. So this is a continuous function. So let us see the proofs of these statements. So for the first one, let V be an open subset of Y, and then if you compute f inverse V, because f is a constant function, then you will have two possibilities. So either f inverse V is the whole of X when y naught belongs to V, or it is the empty set if y naught does not belong to V. and in both cases this belongs to the topology on X, because both X and the empty set are open. So we see that the constant function f is continuous. Okay, and the second one, for the second one we have the map J from A to X. So if U is an open set in X, then J inverse of U is simply the set A intersection U. You can just verify this, it is easy to verify, and I leave it to you as an exercise. And now notice that this is precisely the kind of open sets that are available in the subspace topology. So this is open in the subspace topology on A, and this means that J is continuous. Now we have three more ways to construct continuous functions. So the first one is just by composition. So if f from x to y and g from y to z are continuous, then the composition of these two functions is a continuous function. The fourth way is to have a local formulation of continuity. What is meant by a local formulation? So if a function f is from x to y is given, then it is continuous if X can be written as a union of open sets U alpha. So here U alpha are open in X, such that the restriction of f to the U alpha is continuous for each alpha in J. So this is what is meant by a local formulation, because you are only considering small open sets on which the restricted function is continuous. So this is why it's called local. And finally we have the pasting lemma, which says that if X can be written as the union of two closed subsets A and B, so X is equal to A union B, where A and B are closed in X. And now if we consider functions f from A to y and g from B to y, continuous functions, such that they agree on the intersection A intersection B, so fx equal to gx for all x in this intersection, then the function h from x to y, which is kind of pasting together both f and g. So hx is defined as fx if x belongs to A, and gx if x belongs to B, and this is a continuous function. So let us look at the proofs of these statements one by one. So for the composition of functions, we have x from x to y and g from y to z are continuous, and then take any open set, say W in Z, in this is open in Z, okay, and then we can consider what is G composed with F inverse of this open set W. So if we can show that this is open, if we can show that this is an open subset of X, then we are done. Then this implies that G composed with F is continuous. So what is G composed with F inverse? G composed with F inverse of W? Well, this is nothing but F inverse composed with G inverse of W. So I want you to check this relation, and it is just a set theoretic relation with respect to inverses. Okay, so this is nothing but F inverse of G inverse of W. Now W is an open set in Z, so G inverse W belongs to the topology tau y on Y, because G is continuous, and because F is continuous, then this belongs to the topology tau x in X. So the whole thing belongs to tau x. So this means that G composed with F is continuous. Now let us see the local formulation of continuity. So it says that a function f is continuous if x can be written as a union of open sets u alpha such that the restriction of f to each u alpha is continuous, okay, for each alpha. So let us see a proof of this fact. So suppose that we take V, an open set in Y, then what is F inverse of V? Now, since X is a union of all these U alphas, F inverse of V is nothing but the union of F inverse V intersection U alpha, alpha in J. So this is again a set theoretic relation that I want you to check this. Not very difficult. So, but now notice that F inverse V intersection U alpha is nothing but F restricted to U alpha inverse of V, and because both of these sets are nothing but the set of points in U alpha says that f of x belongs to V. Okay, both of these are the same set. So now since we have considered f, the restricted function to U alpha is continuous, so this means that the inverse image of V under the restricted function belongs to tau x, and this is for all alpha in J. So this means that f inverse V is a union of open sets in X, and which means that f inverse V is open. So this proves that f is continuous. Okay, so this proves 4. Now for the last one, for the pasting lemma. Now let us look at the pasting lemma, which said that if X can be written as the union of two closed sets A and B, and F from A to I and G from B to I are continuous functions which agree on the intersection A intersection B, then the function H, which is given by fx if x belongs to A and gx if x belongs to B, is a continuous function. Here h of course is a function defined from x to y. Okay. Now just before we go to the proof, just let me give some remarks. So the first remark is that the requirement f restricted to A intersection B is equal to G restricted to A intersection B is necessary for H to be well defined. So what I mean by this is, for example, suppose that x equals r. So for example, x equals r, A equals minus infinity to 1, and B equals 0, closed interval, closed at 0, 0 to infinity. So x equals A union B, and A intersection B is precisely the interval 0 to 1. Now if you take fx equals 3x and gx equals 2x, so f is a function from A to r, this is y, g is a function from B to r. So what does it look like? So you have the plane and you have the points 0 and 1 here. So A is the interval from minus infinity to 1, and B is the range from 0 to infinity. So the intersection is precisely the closed interval 0 to 1. And now if you look at the function 3x, then it is something like this. You know, you have this function fx here, and on the other hand gx is a function which looks like this. So on the intersection, fx and gx are not the same, and this means that at some point, let's say half, you have two different values for, if you want to define this function h in this way, then you will get two different values of the same function, which is not allowed. This is not a well-defined function. So this means that this requirement is necessary for h to be well defined. On the other hand, you also need some restrictions on the sets A and B. For example, I will give you an example where A and B are not closed and all the conditions are satisfied, but h is defined this way, is not continuous. For example, so this is the second remark, that A and B cannot be arbitrary subsets for the pasting lemma to hold. So for example, if you take x equals r, A to be the rationals and B to be the irrational numbers, then A intersection B is the empty set. So if you take f from Q to R defined by fx equals 1, the constant function, and G from R minus Q to R defined by gx equals 0, then these are constant functions and they are continuous. As we have seen in the first part, they are continuous functions, and they agree on the intersection because the intersection is empty, so that condition is vacuously satisfied. So f A intersection B is equal to G A intersection B is vacuously true. And so if you define hx to be 1 if x belongs to Q, and 0 if x belongs to R minus Q, then this is not a continuous function. Why is this? Well, because, for example, if you take the inverse image of the set minus half to half, then the only thing that you will get here is the set of irrational numbers, and the set of irrational numbers is not an open set, not an open subset of R. Why? Because if you take any irrational point, let's say R in R minus Q, then any neighborhood AB, basic neighborhood AB containing this irrational point will have rational numbers. So there exist rational numbers Q in this interval AB. So no basic neighborhood will be completely contained inside R minus Q. Therefore, this is not an open subset, and so H is not continuous. So this is the proof that H is not continuous. And now let us look at the proof of the pasting lemma. So to prove the pasting lemma, take a closed subset C in Y, then C is a subset of Y, so it is a closed subset. Now H inverse of C is nothing but F inverse of C union G inverse of C. So again, this is a set theoretic equality, and I want you to check this and leave it as an exercise for you. Now F is continuous. F is continuous. This means that F inverse C is closed in X, and because closed in A, because f is a continuous map from A to Y, and since A is closed in X, this means that f inverse C is closed in X as well. So this is again about subspace closed subsets in the subspace topology, and I didn't prove this earlier, and this is easy enough for an exercise for you to show. Okay, similarly G inverse C is closed in X, and this means that H inverse C is closed. It's a union of two closed sets, so H inverse C is closed in X, and this means that it for every closed set, the inverse image of closed set under H is closed. This means that H inverse of any open set is open in X for any open set V in Y, okay, in tau Y. So this is just because H inverse V complement is equal to H inverse V complement. Okay, so it is enough to show that the pre-image of closed sets under H is closed. So this concludes the proof of the pasting lemma. Finally, let us see two other ways of constructing continuous functions. So the first one is functions into product spaces. So for example, if you have two functions f1 from x to y and f2 from x to z, then the function f from x to the Cartesian product y cross z, given by fx equals f1x comma f2x. This is a point in the Cartesian product, and this is continuous if and only if both f1 and f2 are continuous. And this is a useful thing that we can use many times. This is a very useful result. Now, for continuity of real valued functions, so if you have f and g from a topological space X to the real line, and they are both continuous, then the functions f plus minus g, f into g are both continuous, and if gx is never 0, then the division f by g is continuous. So here, what are these functions? F plus minus g applied at a point x is nothing but fx plus minus gx. Similarly, f into gx is nothing but fx times gx, and similarly f by gx is nothing but fx by gx, and this is only defined when gx is never 0. So let us see a proof of these two properties. So let us see a proof of the sixth property. So here f1 and f2 are given functions, and f from x to the Cartesian product is formed using these two functions f1 and f2 like this. And now suppose that we have the coordinate projections pi1 and pi2. So we have seen these maps before. So this map takes xy to x, and this map takes xy to y. Now if f is continuous, notice that we are always taking the product topology on the Cartesian product. So if f is continuous, we have that f1 is a composition of pi1 with f, and f2 is a composition of pi2 with f. Okay, so this is now a map from x to y, and this is now a map from x to z. So this means that f1 and f2 are composition of pi1 and f, and pi2 and f. Now notice that both pi1 and pi2 are continuous maps, since we have already shown that the product topology is the same when you are when you take the sub basis with respect to the inverse images of pi1 and pi2, so they are continuous maps. So this means that f1 and f2 are continuous, because from the third statement above, composition of continuous maps is continuous. So f1 and f2 are both continuous. Now suppose that let f1 and f2 be continuous, and let's take open sets u in y and v in z. So what is f inverse of u cross v? Well, f inverse of u cross v is nothing but f1 inverse u intersection f2 inverse v, and this is again a set theoretic identity, and I want you to check this out by yourself. Just prove that each one is a subset of the other. Okay, and since f1 and f2 are continuous, well, this is an open set in X, and also this is also an open set in X, so it is an intersection of open sets. So this is an open set, and this is enough because u cross v is a basic element, is a basis for the product topology. This is a basis element for the product topology, and we have seen that it is enough to check that the inverse image of basis set is open for continuity. So this means that f is continuous. Finally, let us look at the last property, which is about real valued functions. So for this, let us take two continuous functions f and g from x to r, and let us define a map H from x to r cross r, the Cartesian product, by taking hx equals fx gx. So by the previous statement 6, we have that h is a continuous function, and now we can write f plus g, which is from x to r, as the composition well, first take h from x to r cross r, and then take the addition operation on r. So what do you get here? So x goes to fx gx, and then it goes from r cross r to r, and then the addition operation is simply fx plus gx. So this is nothing but f plus gx. And now we use the fact that the operations addition are from r cross r to r, subtraction from r cross r to r, and multiplication from r cross r to r. These are all continuous functions. So you might have seen this in a calculus course, and it is possible to also prove it using the methods we have described now. And you will find an exercise in Munkres which gives you some details about this proof of these results, and this is exercise, and a proof of these results is outlined in exercise 12 in section 21 in Munkres. So you can check that out and try to prove it yourself. And here we are going to use this. So for example, when you write f plus g as a composition, and both h is continuous and the plus operation is continuous, so f plus g is a composition of continuous functions, and this means that f plus g is a composition of continuous functions. So this means that f plus g is continuous. Now for the only remaining part is the division operation, and here we use the fact that the quotient, the division operation from r cross r minus 0, we have to remove 0 because division by 0 is not allowed, and this is also continuous. And then f by g, when gx is never 0, f by g is the following map. So you take x, then you apply h again from r cross r to r minus 0 now because g is never 0, and then you apply this division operation to r, and so you will have f by g is also a composition of continuous functions. So this is a continuous function. So this concludes the proof of our theorem.